structure, it looks something like this. I'm hoping you see there's 5 groups around it. I'm hoping that you're picturing something that looks like this. So we have the 3 things and then the 2 things. And this thing is called a trigonal bipyramid, trigonal bipyramidal. So if I were to ask you what the bond angles are in here, you would list 3. There's 180, there's 120, and there's 90. You would list all 3. If this bond was polar, it is, the molecule still would be nonpolar. The way you can do that is by looking at each section. Again, pretend you're the red thing. These are 3 burly triplets with a rope tied onto you, and they're all pulling in equal amounts. You see that the red ball won't move. And then you've got actually a quintuplet of burly guys. And the other 2 are pulling you this way, and you see that these 2 forces cancel. So it's a symmetry argument, or it's this guy pulling on you with ropes argument. So there is no positive end to this and negative end to it. We say the molecule is nonpolar. It has 90, 180, and 100 degree, 120 degree bond angles. Now, let's talk about hybridization. You point to an atom, and you say it's got 1, 2, 3, 4 groups. 4 groups, 4 hybrid orbitals. The type of orbital that chlorine is using would be sp3. Right, sp3. This lone pair is an sp3 hybrid orbital. This lone pair is an sp3 hybrid orbital. This lone pair is an sp3 hybrid orbital. And there's an sp3 hybrid orbital right here. So, if I was actually making this model correctly, I would have the chlorine looking like this, and I would have my, you guys know you're going to be playing with models all week in lab today? Yeah, it'll help. So the chlorine is actually a tetrahedron. It's using sp3 hybrids, and these lone pairs are arranged in a tetrahedral way. So that would be that bond right there. And I would have to, actually this one. I would have to do the same with all of them, but let's just pretend they're there. So the chlorine is sp3 hybridized because it has 3 groups. Do you even need the model to know it's sp3 hybridized? No. 4 groups. 1, 2, 3, 4, sp3 hybridized. Okay, what about phosphorus? So you look at it, and it's got 5 groups, yes? 5 groups means 5 hybrid orbitals. S, D, that gives us 4, D. So since we have 5 groups, we need 5 hybrid orbitals. 1, 2, 3, 4, 5. The name of those hybrid orbitals is, yes, sp3d, or, depending on which book you're reading, dsp3, don't care, don't care, don't how do they arrange themselves? As far away from each other as possible and not compete. What do these do? Not covered in this class. So who gets to have sp3b2 hybridization? Elements in the first period, no. Second period, no. Third period, yes, because n equals 3 means you can have d orbitals. So you see this with phosphorus, sulfur, chlorine. You'll see sp3b, sp3b2 hybridization because they have 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 12. 2, 4, 6, 8, 10, 12 electrons. It violates the octet rule. What did I say about the octet rule? It only applies to things in the second period because there are no d orbitals in the second. There's no 2d orbitals. So it violates the octet rule, but there is no octet rule for chlorine, sulfur, and phosphorus. Okay? So the different kinds of hybridizations you can have are sp, sp2, sp3, sp3d, and sp3d2. That's it. There are no other forms of hybridization that you will ever run into in any chemistry class. There is no hybridization sp3b3. There aren't any molecules that look like that. If there were a molecule, it would look like that, right? 1, 2, 3, 4, 5, 6, 7, 7, 7. 1, 2, 3, 4, 5, 6. Oh, let's pick that one up there. And it would be called sp3b3 hybridization. But we don't have any molecules that look like that. So in your mind, you can imagine that there's sp3b3, but if there's no example of it, then there's no example. Okay, last thing I want to talk about is a little touch on resonance. Look at carbonate. And this actually is kind of a lot to get your head around. So if you can't get your head around it, okay, complicated. You may miss that problem on the test, but there's extra credit, only 3 points. I think I'm going to do 3 points per question, so it'll be 33 plus bonus questions, because asking somebody what's the bond angle is like, look at the Lewis structure, count the groups, blurt it out. It's not calculate, like the thermodynamics one where you were doing Hess's law things, and those took forever. So on the last test, I made the test shorter and made each question worth 4 points each, gives you more time to do it. In this one, I'll go back to the first test, which is 3 points each. So if you miss a question, it's no big. Okay, so here's my question. What is the OCO bond angle? Do you know why I put the negative charge here, by the way? 1, 2, 3, 4, 5, 6, 7. It's supposed to have 6. Has 1 extra electron and a minus 1 total charge. In higher level chemistry classes, they don't even put the lone pairs because you're supposed to know they're there. So occasionally I'll leave them off and go, oh, gotta throw back. 1, 2, 3, 4, 5, 6. Supposed to have 6, has 6. Neutral. Okay, so what I said here is the CO bond lengths are all the same. If there was one that had double bond, it would be shorter, and it would have 2 different bonds, short, long. But all the bond lengths would be the same. What You get pi electrons? You get that term? It's the overlap in a carbon-carbon double bond. So these electrons, sigma electrons, are localized where they are. It's these pi electrons that are moving. It's the carbon-carbon double bond that seems to not be in one place. You have to draw three structures to show the structure of this molecule, because that double bond isn't in one place, it's everywhere. So, what is going on with the hybridization? You've got to see, do you see that in all cases it always has three groups around it? So it's always got three groups. It is always, always sp2 hybridized, yes? If we look at this oxygen, 1, 2, 3 groups, three groups. Here it is right here. And it's got that p orbital, yes. There's a sigma bond, there's a pi bond. But what about that oxygen, and what about that oxygen? If you just look at this structure, it looks like this is sp3, and this is sp3, and this is sp2. Again, they're different, but they're not different. So what's going on? Well, what if we say that this is also sp2 hybridized, and this is also sp2 hybridized? We just won't hybridize it to sp3, we'll hybridize it to sp2. Do you see that all of these p orbitals can now overlap at the top and the bottom? So these two electrons, which in this picture I show here, in this picture I show here, in this picture I show here, are actually spread out along these 1, 2, 3, 4 orbitals. Where are they? They're everywhere. I can't draw a Lewis structure showing that, but now that you've learned about localized electron molecules,